Hi, Assalamualaikum and welcome back to my channel Physics from 5 KSSM. So now we continue 4.2 Electromagnetic Induction Part 2. In this video, I will discuss on two learning standards. The first one, determine direction of induced current in straight wire and solenoid. The second one, design a DC and AC generator. How to determine direction of induced current? Let's look at activity 4.12. For the first part, we discuss on direction of induced current in a straight wire. Apparatus required: thick copper wire, a pair of magnetometer, sensitive center zero galvanometer or digital multimeter, a dry cell with holder. This is a dry cell with holder, 1 kilo ohm resistor, and switch. Material connecting wires with a crocodile clip. So for the first part, we want to discuss and understand how the galvanometer pointer works. Before we discuss about induction that caused by copper rod, let's understand the deflection of galvanometer once galvanometer is connected in the circuit. Okay, if you look at here, this is a zero-centered galvanometer. Connect to a dry cell. So you can see a dry cell is marked X and Y. This is the dry cell holder, so we just mark X and Y here. This is a switch. This part we call it external circuit, and it has a resistor here, carbon resistor. Okay, and then in the battery holder we put one dry cell. Let's observe what happens to the galvanometer pointer when the switch is on. So for the first part, the positive terminal is at Y. The battery is placed so that the positive terminal of the battery is at point Y, and the negative terminal of the battery at point X. Let's observe the direction of deflection of galvanometer pointer and also direction of current in the battery. Meaning either is X to Y or Y to X. Okay? Observe what happens when the switch is on. Logically, we have discussed before, current always flows from positive to negative. But in the dry cell, the current is flowing from X to Y. So look at deflection of the pointer. When Y is connected to the battery at positive terminal and X negative terminal, in external circuit, the current will flow from positive to negative. In the battery, is from X to Y. When in battery is X to Y, so you can see deflection is to the right. So we get for the first part, for this one, direction of deflection of galvanometer pointer is to the right. Direction of current in the battery is X to Y. What happens if the battery is reversed? Now Y is negative, X is positive. Observe what happens to the galvanometer pointer when the switch is on. Of course, the current will flow from positive to negative in external circuit. How about in the battery? It will flow from Y to X. When flow from Y to X, pointer of galvanometer will deflect to left. Okay, now let's fill in all the answer here. Okay, dry cell, positive terminal at Y, negative terminal at X. Direction of deflection of galvanometer is to the right. Direction of the current from X to Y. If dry cell is reversed, negative at Y, positive at X, galvanometer pointer deflect to the left. Direction of current in the battery is Y to X. Okay, that's the explanation why the pointer deflect to left. So you must understand how the galvanometer pointer deflects in order to understand the next activity. Okay, the next activity is the copper wire move upwards and then move downwards. When the copper wire is moved upwards, which direction the galvanometer pointer deflect? How to determine direction of current flowing in the circuit? We can apply Fleming's right-hand rule. According to Fleming's right-hand rule, the thumb represents the motion of the copper wire upwards. The forefinger represents magnetic field always pointing to south, and the center finger represents direction of current. By using Fleming's left-hand rule, we will determine that direction of current is from Y to X. So when Y to X, thus the pointer will deflect to left. Okay, next, the copper wire move downwards. Apply Fleming right-hand rule. Your thumb is downward, the forefinger pointing south, the center finger showing that the current is flowing from X to Y. The galvanometer pointer will deflect to the right. So let's discuss further on Fleming's right-hand rule. In the case of wire move in magnetic field or permanent magnet, we can use Fleming's right-hand rule to determine direction of induced current. The thumb represents motion of wire, either upwards or downwards. The forefinger represents magnetic field always pointing to south, and the middle finger direction of induced current. Try to relate direction of magnetic field lines, direction of motion of copper wire, and direction of induced current by using Fleming's right-hand rule. The relationship is the three fingers, motion of wire, magnetic field, and induced current are perpendicular to each other. Suggest other ways to change direction of induced current other than that direction of motion of copper wire. Just now we discussed that different direction of motion of copper wire, it will cause the galvanometer to deflect in reverse direction, meaning direction of motion affect direction of induced current. Another factors that will affect direction of induced current is the polarity of magnet. If we reverse the polarity of magnet, direction of induced current will be reversed, thus the galvanometer readings also reverse. Let's look at these two situations. For the first situation, the copper rod is moved upwards. The second one, the copper rod is at stationary, but the magnet is moved downwards. Look at the reading of the galvanometer. the pointer of galvanometer deflect to the left, same direction. Why? Because motion of the magnet downwards actually is equivalent to motion of the wire upwards. There is relative motion for both cases. By using Fleming right-hand rule, we determine that both will produce same direction of induced current. Fleming's right-hand rule is applied for the copper wire, not to the magnet. So this one you need to, if magnet move down, so you need to assume that your thumb is upwards. The copper wire is moving up. Okay. Let's look at activity 4.13 to study direction of induced current in solenoid. So we have here solenoid, bar magnet, sensitive center zero galvanometer or digital multimeter, material connecting wires with crocodile clips. I have discussed in my previous video, when a bar magnet is moved towards a solenoid, the solenoid will cut the magnetic field lines of the bar magnet, thus produce induced EMF across the solenoid. So which direction the current will flow in the solenoid? So direction of current flow in the solenoid, we need to apply Lenz law. According to Lenz law, direction of induced current in the solenoid here always oppose the effect that produce the change in the magnetic flux. What is meant by that statement? For example, north pole of the bar magnet is moved towards NA of the solenoid. In order to oppose the effect that produce the induced current, NA will produce repel force. To produce repel force, NA must be same pole with the bar magnet. So when north pole of magnet is moved towards NA, NA will become north pole in order to oppose the effect. When the pole of the solenoid at NA is north, meaning direction of current flow in the solenoid is anti-clockwise direction. So when anti-clockwise, you can mark direction of current flow in the circuit. Galvanometer pointer will deflect. Current flow in the solenoid from right to left. Thus, the pointer will deflect to left. Now, let's say the north pole is moved away from NA. According to Lenz law, NA will become same pole as the magnet to oppose the effect, meaning attract the magnet. So NA become south pole, direction of current is clockwise in the solenoid. When clockwise, the current is flowing from left to right. Thus, galvanometer pointer will deflect to right. Okay, look at this one. Let's say we use the south pole of the magnet. South pole is moved towards NA. To oppose the effect, NA will become south pole. Direction of current is clockwise. Thus, current flow from left to right. Galvanometer pointer deflect to right. When south pole of the bar magnet is moved away from NA, NA will become north. Direction of current is anti-clockwise. Thus, the current flow from right to left. Galvanometer pointer deflect to left. We will discuss more on this one. Let's let's say for the first part, we have discussed before, when north is moved towards the NA of solenoid, galvanometer pointer deflect to left. NA is north pole. When north move away from the NA, galvanometer pointer deflect to right. NA is south pole. For the second part, we use the south pole of the bar magnet. South move towards NA. NA becomes south. So current flow from left to right. Galvanometer pointer deflect to right. South move away. NA become north. Direction of deflection of galvanometer pointer deflect to left. Let's discuss some questions. What is the effect of motion of bar magnet on polarity of magnet at NA of the solenoid? Polarity of NA solenoid is reverse when direction of motion is reverse. Predict the polarity of magnet produced at NA when south pole of bar magnet push towards it. This is what we already discussed. Polarity of Na is south pole. When south pole pull away, polarity Na is north pole. So you must understand Lenz law in order to determine direction of deflection of galvanometer pointer or to determine direction of current in the solenoid. Let's discuss more so that you will understand better the situation. According to Lenz's law, the induced current always flow in direction that opposes the change of magnetic flux that causes it. So for example, A, north pole is moved towards the solenoid. Induced current produces a north pole at end of the solenoid to repel the magnet moving towards the solenoid. If moved towards, it will become same pole in order to produce the opposed effect. So when this end is north pole, direction of current, when you look exactly from this side towards the solenoid, direction is anti-clockwise. So you continue to mark direction of current. You can see current is flowing from right to left. Or we can say north to south, right to left. So this one will cause pointer or galvanometer to deflect to left. Look at B. Let's say south pole of bar magnet move towards the solenoid. Induced current produces a south pole at end of the solenoid to repel the magnet moving towards the solenoid. Move towards, it will become same pole to oppose the effect. So this end is south pole, direction of current is clockwise. So you continue to mark direction of current in the wire. You will find that direction of current in the solenoid is from left to right. Thus, the galvanometer pointer deflect to right. C. Let's say north pole is moved away. So what happens? Based on the Lenz law, induced current produce south pole at end of the solenoid to attract the magnet moving away in order to oppose the effect. Thus, if this end is south, direction of current is clockwise. You continue to mark. You can see current flow from left to right. Thus, pointer of galvanometer deflect to right. D. South pole of bar magnet move away from the solenoid. Thus, end of the solenoid here become opposite pole. Okay, to attract the magnet moving away from the solenoid. This is north, So direction of current is anti-clockwise. You look at the solenoid, direction of current is right to left. That's the reason why galvanometer deflect to left. You must understand how to apply Lenz law in order to determine direction of induced current. That's all my video today. Thank you for watching. Bye.